Welcome to another Science Live. We're going to be talking mainly about the project that you're working on this week. So we're going to look at this project here, which is analyzing a mechanical system. And ultimately what you're doing here is you're applying some of your understanding that you've learned so far to start looking at how machines are actually made, right? Every single thing in the world that you use that's a tool, somebody designed it, and they designed it by understanding the physics of how mechanical systems work. And that's what you're learning as well. So today what I'm going to do is show an example both with a bike and also with a wrench. And we're going to just kind of talk through this project a little bit. But before we do that, I'm just going to draw your attention to the slides that are here for the week. Now, a lot of you have already started looking through these. Some of this is review, just talks about simple machines. And then from about this slide onward, we start to talk about complex machines and analyzing complex machines. So here we see a bike. The idea is that a good drawing of a machine shows the parts that are there and their relative sizes and how they might connect together. When we're thinking about a complicated system, right? So I've got my bike upside down here, so it's easy for us to play with it a little bit. When we're thinking about a system like this, we're thinking about sort of what are the different functions of that system. And we're thinking about what are the inputs and outputs of each of those different functions. So when you're riding a bike, you've got kind of three things that you're doing to the bike at any given time. You're doing some pedaling of some kind. You're doing input on the pedals. You are doing input on the brakes. So the brake levers are allowing you to control the braking on the bike. And then, of course, you're turning the handlebar as well, and that's allowing you to do some steering. Of course, there's other techniques involved in biking, but those are the main systems in a bike. And so when you're starting to think about a complex system, you want to start thinking about what are the main functions, and usually each of those functions then forms its own system. So you can start talking specifically about the pedaling system, what it is that gives you power with your bike and gets you moving. You could talk about the braking system, right, that runs back to the wheels and allows you to stop. And so that allows you to start to break a complex system apart as soon as you start to think about what are the different functions. And even simple machines, or simpler machines, I should say, like, for example, a wrench, these are still made of multiple systems. So like this wrench, for example, it has two systems. It has a system that allows you to adjust the size of the wrench and adjust the, what size bolt you're going to be tightening. And then it has a second system, which is how you actually turn that tool when you apply it. And so you can break it into those two different functions. Even a hammer has two different systems. It has a system for putting nails in and a system for prying nails out. So that's a starting point to think about what are the subsystems that make up a machine. What are they taking as their inputs? And when we're talking about inputs, we're talking about a force and a distance, right? So when I'm pedaling on a bicycle, my input is the force that I'm applying to the pedals and the distance that I'm pedaling through. So every time I do one rotation, my feet move a certain distance and I'm pushing as I do that, so I'm applying a force. So that tells me, of course, that I'm doing work to the bike. I'm delivering energy to that bike because I'm applying a force over a distance. And that energy in this case is flowing through the bike, right? If we're looking at specifically just the gear system, the energy of my foot moving and pushing on the pedal is going through these chains to the back gears and being delivered to the wheel, which is moving, so it's covering a distance, and it's also applying a force. When this bike is pointing the right direction, it's applying that force to the ground so that you can develop some acceleration. So this is the main idea of looking at analyzing a mechanical system. If you were to look at, for example, this wrench here, and you were to look at this this adjusting mechanism, you can think in the same way. I'm applying a force and a distance to this little adjusting mechanism, and that's applying a force and a distance to this. You'll notice that the way this is designed, I can apply a very easy force to make it open and close. But if I try to work it from the other end and make it close this way, it's actually impossible. I can't apply enough force here to get the other end to go backwards. And so this is kind of a deliberate design for this machine. And then similarly, when I'm using it as a wrench, I'm applying a force and a distance just as a lever, and the thing that I'm tightening is being heightened with a certain force over a certain distance. So once again, there's always an energy going in at one end, which is a force times a distance, and an energy coming out, which is a force times a distance. And that's what we're talking about when we talk about work and energy. We're talking about that flow through a system. And then, of course, the forces we can compare. We can compare how much force we put in here and how much force we get out here. And that is a thing called mechanical advantage. And we can also do the same thing with how far the system moves. So how much this part here turns in the middle versus how far the handle moves. And that gives us our speed ratio. So that's basically everything when we're talking about machines. And everything about machines are designed for these things, from things that are fairly complicated, like a bicycle, things that are fairly simple, but even more complicated things, right? Like a car. If you understand basic mechanical principles, then you understand every part of a car and why they fit together the way that they do. So this is analyzing mechanical systems. Let's just look at the assignment here for a second. Feel free to ask any questions if you have them. So one of your goals is simply to be able to kind of visualize how the parts of a system fit together. You're paying attention to the specific parts. Like in this case, you'll notice that this tool, the wrench, is made of 3 parts. It's made of this kind of solid handle in the top part, and then this movable bottom part, and then the screw. So there's kind of 3 parts here, and a good diagram would show those 3 parts and show that they sort of can move independent of each other. We talked about inputs, outputs, energy sources in here, and that's kind of the major thing we're thinking about when we're designing mechanical systems. Is like, where am I getting my energy from, and where's it going, right? So when I'm using something like this, the energy is coming from me. It's coming from my muscles specifically. It's coming from the energy of my cells metabolizing, right, to my muscle cells to be able to expand and contract. And of course, that's coming from, you could go on, right? The sugar in my blood, and that's coming from the food I ate, right? So you can talk about how energy flows, but when we're talking about a machine, we're specifically talking about like the force I put in and the force that comes out the other end. Let's see. We talked about subsystems. If you choose a complicated machine for your machine, then you might want to focus really just on one subsystem. Like you might want to outline all of them. Like a bike, you could talk about the gear system. You could talk about the braking system. You could talk about the handlebars or whatever. But you might want to just focus on one, right? So in this case, this is focusing on just the brake lever, just that individual system there on one end, and then the braking system, one type of braking system for a bike that sort of squeezes the rim of the bike here. This one doesn't have that. It has a different type of brakes, but some bikes you'll see where there's actually something that just kind of squeezes on this metal rim, and that slows the bike down. We're going to really look at this system though, because I think this is the most interesting system. This is the like the pedaling the gear and chain system. And just looking just alone at this system right now, you've probably already seen the slides. You've already probably seen how this breaks down. But take a moment right now and just kind of consider, how many different simple machines do you see put together to form this system? If we're talking just sort of the pedaling and the drive system of the bike. It kind of depends on how you break it down, right? There's some very obvious ones. For example, there's the gear system here, which is sort of like a wheel and an axle, but there's sort of 3 gears there. So it's kind of like 3 wheels and axles because you can change between settings. You might see that there's sort of levers here that are very obvious. But there's maybe some less obvious ones, like this system here at the back that also controls the gears. This is made of multiple levers connected together. Like there's one lever attached to another lever attached to another lever. So, I mean, this is, again, a very complicated system. And you could look at each of those individual components and you could look at the force and the distance. To be honest, I don't really know the answer. It just kind of depends on how you divide this system up, right? There's the chain, which is like a pulley system. But again, there's multiple gears here, and each of those gears is kind of like its own simple machine. So the point here is that it's very complicated, and you could go very complicated with each of those components. So what you could do is you could pick one of these things and you could talk about it. But what I think is more interesting with a system like this is, with all of these simple machines linked together, to look at like the full flow of energy in this bike. So when I'm pushing on the pedals of this bike, thinking about how quickly the wheel in the back goes. So right now I have like this on the highest possible gear. And you notice that I don't actually have to turn the pedals very much to get the bike wheel to move quite a bit. It's a good example of sort of the idea of a speed ratio. And that this is kind of going to make me faster. This is a great gear to be on if like you're on flat ground or you're going downhill. But it's on a very high gear, and I can change it the other way to make it on a low gear. And we'll look at it. We'll take a moment and we'll actually analyze this system, and we'll kind of do some math on it in just a moment. That's kind of where we're going to go towards the end of this, as we're looking at these mechanical systems. We're talking about linkages, so we might talk about the chain, for example, and we might also talk about the materials, right? So as we look at this, we can talk about all the simple machines that fit in it. We can talk about the way that those simple machines are linked together. And then we can also talk about like what this is actually made of to allow each of those parts to work really well. Like which parts are really quite strong, whereas which ones are like designed to be a little softer or more flexible, for example. So that's like the major part of this assignment, right? And then what you could also talk about is you could talk about like how a bike has changed throughout time. Right, because this isn't always how bikes have looked. So you could talk about how each of those systems have evolved over time and how we've gone from one design to the next design. And that's sort of another angle that you could use to analyze machines. It's more of like a historical angle. But nevertheless, when you consider how things evolve through history, you end up realizing that it tends to be about things like getting a better mechanical advantage or getting a better speed ratio or a better efficiency. And so they tend to go back to these very same mechanical concepts, even if you're looking at them historically. So that's going to be the entirety of your project, right? Is to like look at all those different parts, all those different pieces. And then I think there's a bonus at the end, and that's about calculating a speed ratio and a mechanical advantage. And I'm going to show you that in just a second here. It's like a bit of a more advanced thing, but it's also a really good review of the work we did before the break. So let's look at analyzing this as a mechanical system, talking about speed ratio and mechanical advantage. So what I'm going to do is I'm going to keep this on this highest gear. And what I want you to do is just watch the ratio as I turn this bike. So notice I've turned this so that the text is at the top. Unfortunately, I'm kind of probably mirrored for you right now, or maybe you've got two of me. I don't know, whatever. Anyway, so there's this text up here, and then I've also got the text up here as well on the pedal. So watch, I'm going to turn this pedal through the system, and notice that as I turn this around, you can count how many rotations the back wheel makes. So that looks like one rotation. There's two rotations, three rotations. How many rotations is it going to make to once I finally get the pedal back to its final location? It's going to be about 4 rotations, right? So what we notice here is that this part of the system, every time I do one rotation of this part of the system, I get 4 rotations of the wheel. So there's like a 1-to-4 ratio involved there right away, right? Every time I pedal once, I get 4 turns of the wheel. So again, that's going to make me go quite quickly. The disadvantage is it's actually quite hard to turn this system just even on its own against its own resistance. And if you've ever been on a bike and went up a hill, for example, and been in the wrong gear, you notice very quickly that you can't actually put in enough force, and then you like fall over. So this is a good gear for speed when you can apply the force, when you're like on a flat ground and you can stand and you can kind of pump the pedals a little bit, whereas it's not going to be very good when you're struggling to apply that force, like climbing a hill, for example. So this is like a 4-to-1 ratio, but we could go further than that if we wanted to. And we are going to, because like, why not nerd out a little bit about this? So let's consider, it's not just that this is going to make you 4 times faster, because this back wheel is actually significantly bigger than the rotation of this pedal. So I want to try something, and you can tell me if I'm being too nerdy. So, all right, cool. So, all right, so let's just look at this for a second. So when I turn this pedal, okay, it starts right about here. And when I turn this pedal, it goes through a circle. Oh, I'm not doing a terrible job of actually tracing out a circle. And it goes back up around like this, right? Okay, that's awful. Let's try that again. It's very experimental. So it's going to be kind of like a circle that gets traced something like this. So the pedal goes through a rotation like that. And meanwhile, the wheel goes through, when it does one rotation, it goes through a circle like this. So, and we also know that the wheel already goes 4 times around every time that the crank goes 1 times around. So this does 1 rotation in blue and the purple one does 4 rotations. But they're also different size circles. So we're going to do some math here. And it's just a quick reminder that if you wanted to find like how far around a circle, the distance around a circle, your formula for the circumference is pi times the diameter. So in other words, if you know the width of the circle, then you just multiply it by pi and then you know the distance around. And pi is like about 3, so we'll use about 3. So look at, for example, this back wheel here. So if I measure this, I'm measuring it across, and it's about, I'm going to say 24 inches across. Okay, so I measure that way across. Again, this is probably backwards for you, I think. But anyway, 24 inches. So it's 24 inches across. And so if we do the math, that's going to be a diameter of 24. And we're just going to times that by 3. And so 3 times 24 is like 72 or something like this. So this is going to cover 72 inches. The wheel itself, the rubber of the wheel, is 72 inches around the wheel if we measured it around the wheel. But again, that wheel, when it makes 1 rotation, it's going to go through 72 inches. But if it makes 4 rotations, then it's going to be even more movement. So 72 inches times 4 is 288 inches. So what that's telling me is that this back tire moves 288 inches when it makes 4 rotations, which is when this makes only 1 rotation. So now if I were to figure out, okay, well, how far does this part of the system move when I make 1 rotation? So as I go through and I make 1 rotation through this system, well, let's just do the same math here. So let's measure across a circle here. And as I measure and turn to there, it's about 12 inches. So the diameter of this circle is about 12 inches. And so again, I'm just going to go 3 times 12 inches, right? So 3 is about pi. So that means that the distance around this, 3 times 12 is 36. So this is 36 inches around this circle. Okay? Stay with me here for a second. So we've got 2 parts of the system. They are linked together. They move together. One of those parts of the system turns once and covers 36 inches as it does so. One part of the system turns 4 times and actually goes 288 inches as it does so. And so if we compare these 2 numbers, you can see one is a lot of times bigger than the other, right? And so we're thinking in terms of ratios here. If I take my 288, that is the number in purple, and I divide by 36, then and you can go ahead and check that. I don't know, it's going to give you like something like maybe 7. I'm just guessing, about 7 or something like that. So what does that tell you? It tells you that this is going 7 times further than your feet are going on the pedals. And so there's a speed ratio there of about 7, essentially. The disadvantage of that, I guess you might say it's a speed ratio of 1/7. The disadvantage then is that it's going to be making you weaker. So it makes you go 7 times faster, but it's going to take 7 times more force to do that, which is why it's bad to bike uphill in that high gear, for example. So that's kind of the idea of the most advanced level of analyzing these systems, right? Is starting to look at the different parts and the ratios that they move with, and like starting to talk about calculating mechanical advantage, speed ratio, or efficiency. But let me remind you that all of this stuff right here is kind of advanced stuff, and it's like extra if you want to. What you really need to focus on for your work is kind of all the simpler parts that lead up to that, right? Of starting to identify the inputs and outputs and seeing how things move and what are the parts made of and how do they all fit together. Okay, so that hopefully should give you an idea. I noticed that we've had a few people that have left. They probably were like, no, thank you. But hopefully that gives you an idea of the full scope of what you could do with a project like this one. Okay. Cool. So that hopefully gives you like a little bit of brain fodder for this project. Thanks for tuning in for us to talk about this and this thing that I've balanced precariously in my workshop here. Feel free to send me a message if you have any questions about this. Once again, you can do this like on paper, do it on poster paper if you wanted to. You can snap a picture, or if you wanted to, you could like record a video like this one too, if you felt inclined. Lots of ways for you to do this project.